Hello, I'm back. Hey, sorry about the last video. It cut me off right when I was in the middle of problem 15, so we're going to pick it up right where we left off. So this is where we were. I had just gotten the same base on both sides, so basically now I just set the one exponent greater than or equal to the other one. I subtracted -3 from both sides. So I would have -1 is greater than or equal to -6n. And then I divide by -6. But remember, when you do that, I'm running out of room here again. We'll take that over to here. You would get a sign change. So you would get 1/6 is less than or equal to n, something like that, okay? Or n is greater than or equal to 1/6 would be another way to write that, and you're all done, okay? So all of these problems in here, though, just to summarize, you always need to get the same base on both sides, and once you have the bases the same, you can sort of cut the base out of the problem and just work with the exponents. So that's true whether it's an inequality like number 12 or whether it's an equality like number 14. Okay? Now, moving on to this next question. The initial number of bacteria in a culture is 12,000. Now, whenever it says the initial number, that means like on day 0. So that means you have a point at 0, 12,000. And then it says the number after 3 days is 96,000, so that's another point, 396,000. Okay, so always think of your data as points. A lot of times your time is your x, and the number of bacteria would be your y. Okay, now we're really doing this just exactly the same way we did this problem right here, number 8. So we're going to go through that whole process again. So we're going to go y equals a b to the x, and we're going to pop in this for y and this for x. So we get 12,000 equals a b to the 0 power. So we get 12,000 is equal to b to the 0 power is just 1, so basically it's just a. So we found our a. Now we write this equation again, y equals a b to the x. That's always where we start. This is my y, this is my x. So I would go 96,000 equals, and this time I can plug a in, so 12,000 times b to the 3rd power. Now I'm trying to solve for b. So the first thing I would do is I would divide 96,000 by 12,000. So I would get 8. So if I divide both sides by 12,000, I'm trying to isolate b right now, I would get b to the 3rd equals 8. And how do you get rid of a cube? Well, you cube root it. We learned that back in chapter 5, I believe it was. And we get b equals the cube root of 8, which is a perfect cube. It just turns out to be 2. Now, if it wasn't a perfect cube, I would put it in a calculator and get a decimal approximation for that. So I have my a, I have my b, so my equation would be y equals 12,000, which is my initial population, times 2 to the x power. So that right there would be the equation that describes the bacterial growth in this problem. Now, after that, we can basically predict how many bacteria there would be on any given day. So if it says how many bacteria are there after 6 days, we would just pop the 6 in for x, so we would do y equals 12,000 times 2 to the 6th power. So 2 to the 6th power is 64, and I multiply that by 12,000, and we have a bunch of bacteria. We have 768,000 bacteria. Now that is called exponential growth, friends, and unfortunately that's kind of what we're dealing with right now with the coronavirus. We are seeing exponential growth, which means we're not just going up a little bit every day. Sometimes we're doubling every day. That's what's happening here, by the way. If you see this 2x, that means every day the bacteria is doubling. There's twice as many people that have it. That kind of thing. So anyways, kind of ties into a lot of what we're dealing with right now. That's the bad thing about it. Now, that would be my final answer to number 18 right there. Okay. If I said how many bacteria would there be after a month, I would plug in 30 days, and obviously that would be some gargantuan number, probably in the millions or billions, okay? Okay, moving on to section 10.2. Now, we're going to start talking about logs. Now, logs are important because they are the kind of the inverse function for exponents. And so if you want to undo an exponent, a lot of times you need to log it. Okay. So write each equation in logarithmic form. Now basically, when you guys did your notes, I'm going to do a little tiny section of notes right here. We should have learned that the log base b of a equals x only if b to the x equals a. So basically the way I always teach this is called the base of the log, and this is called the base of the exponent. So the base stays the base, and the other two guys switch sides. So the a goes over here, and the x goes over there. So every log can be turned into an exponent problem like this, and you can also go backwards. If I give you an exponent problem, you can turn it back into a log. So that's what I'm going to do on this one. So if I want to write this in logarithmic form, I would do log base blank blank equals blank, okay? The 5 is my base, so that goes here. And the other two guys will switch sides, so the 125 will go here, and the 3 will go here. So this log equation is identical to this exponent equation. Okay, those are the same thing, just in different form. Now let's go to number 3. Again, I would go log, my base is 3, and the other two dudes switch sides. So you would end up with that. Number 2, the log, the base is 7, so I put a 7, and then the 1 and the 0. So basically this means 7 to the 0 power is 1. Final one, I would do log. Again, my base is 1/4 of 1/64 equals 3. So again, the base is the base, and the other two dudes switch sides. And you can always turn an exponent into a log. Okay, cool. Moving on to the next page. Write each equation in exponential form. So now we're just going the other direction. So these are real easy. Here's my base, so I just go 6, to this power equals the number right here. And of course we know that's true. 6 to the 3rd is 216. Number 6 would be 2 to the 6th equals 64. The base is the base. This one, 10 to the -5th equals 0.00001. The last one would be 25 to the 1/2 power is equal to 5. Again, your base is your base, and the other two guys switch sides. And we know just from our exponent knowledge that all of those are very true. Okay? So that leads us into this section, evaluating each expression. Now, I don't know how Ms. Brewer and Mr. Clave teach this, but I've always taught this by doing this. Whenever I see evaluate the expression, I always say set it equal to x, and then turn it into an exponent problem and solve it. So let me explain this. So for example, with number 9 right here, I'm going to set this equal to x. Now I'm going to put that into exponent form like the ones I just did right here, okay, just like these. So that would be 3 to the x power is equal to 81. See how that log turned into that exponent. Now, why do we do that? Because we don't know diddly about logs, but we know a lot about exponents. So take the log and make it look like an exponent, and then you'll probably know what to do. Now we're back to what we were doing on the last page. So this would be 3 to the x equals 3 to the 4th. So x is 4. Or in other words, this is equal to 4. Okay? So log base 3 of 81 is the number 4. We just temporarily set it equal to x so we can figure out what it is. Okay, going on to number 10. If I do this one, I would just set it equal to x. So I would get 10 to the x equals 0.0001. Now, what in the world do you do with that? Well, this one's a little confusing, so I'm going to have to drag it over here. So you get 10 to the x equals 0.0001 is 1 divided by, I believe it's 1,000. No, it's 1 divided by 10,000. So this would be 1 over 10000. Okay. Now, who would ever think to do that? You probably wouldn't, but you know you have to get it to be some kind of a base of 10. So I just turn that into a fraction. 1 divided by 10000 on a calculator is basically 0.0001. Okay? Remember, these are called the tenths, the hundredths, the thousandths, and the 10,000ths. So this is 1/10,000th. Now that would be 10 to the x equals 1 over 10 to the, I believe it's 4th power, right? And then you would go, well, that's 10 to the x equals 10 to the negative 4 power. So basically, this whole thing turns out to be negative 4. So the answer to number 10 is negative 4. Okay. Number 11. Set it equal to x. 2 to the x equals 1 over 16. Take it from log form to exponent form. But remember, 16 is really 1 over 2 to the 4th power. I got to get that 16 to be a 2. Now I want to move that upstairs. So this is 2 to the x equals 2 to the negative 4. And then the bases cancel out. So basically this one is also negative 4. Okay? So once you get it into exponent form, you're really back to what we were doing when we were doing these problems right here. Okay, we're trying to get the same base on both sides. Of course, these are a little easier, which is nice. Okay, number 12. You set this equal to x. So you would get 9 to the x equals 1. And we know, you almost can just stop right here and think to yourself, 9 to what power equals 1? Well, the only thing that could possibly be is 0. Because anything to the 0 power is 1. Number 13, you get the equals x, so you would say 8 to the x power equals 4. Now that's going to take a little bit of work. So I'm going to, sorry this is such a mess, but I don't have 2 pieces of paper to work on. I'm going to take that down to here and I'm going to say 8 to the x equals 4. Now I got to turn them both into the same number. This is like 4 to the 1. So 8 is like 2 to the 3rd to the x power. And 4 is like 2 to the 2nd. So we multiply and we get 2 to the 3x equals 2 to the 2nd. Cancel your bases out. So 3x equals 2. So x would be 2/3. So the final answer to 13 would be 2/3. Okay? 14. 14 I'll do down here. I would go 7 to the x power, set this equal to x, sorry, equals 1 over 49. So that's 7 to the x equals 1 over 7 squared. So 7 to the x equals